Hey guys, welcome to problem set 34. We've got some exciting things in this lesson, including summation notation, linear regression, that's a big word, but really just means finding the equation of the line, and decomposing functions. So we'll begin with summation notation. Now this is something new that you have never seen before, so please pay close attention. This symbol right here is called sigma. You don't have to know that that's what it's called, but this is how we do summation notation. Now sigma is going to have three things surrounding it. On top, it's going to have a number. On the bottom, it's going to have some letter equal to a number. And then on the right, it's going to have some expression. Now the idea here is that we are repeating the same expression over and over again using this counter. We're going to count from s equals 1, let's do x, that'll make more sense. X equals 1 to x equals 4. Each time we're going to add what is over here to the right. So if I were to describe each part of this, this is your starting point, this is your ending point, and this is what you are adding. Remember, sum means adding each time. So let's try and do this problem. In this case, I'm going to add 2x each time. But instead of writing 2x plus 2x plus 2x plus 2x, I'm going to plug in the value for x. The first time, x equals 1. So instead of 2x, I plug in 2 times 1. The next time around, I'm going to add 1 and get x equals 2. This is my second time. I haven't reached my ending number, so I'm going to keep going. So we'll plug in 2 for x. Next time, you guessed it, 1, 2, 3. So I'll plug in 3. And the next time I add 1, x equals 4, I know this is my end point, so I won't go any further, but I plug in 4. Now, my problem's not done yet. I must multiply these and add. 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6, 2 times 4 is 8, and that equals 20. So the sum from x equals 1 to 4 of 2x is 20. Let's try another one. Let's try this sum. It's a little bit more difficult. We have the sum when j equals 0 to 3 of 2 to the j over j plus 1. Now it might be helpful for you to write out each value of j before you start. J equals 0, add 1, j equals 1, add 1, j equals 2, add 1, j equals 3. Now I want to stop here because I've hit my stopping number. Now I'm going to write this term with each of my j's plugged in. My term is 2 to the j, 2 to the 0, over j plus 1. So I'll write 0 plus 1. Now since this is summation, I add the next term. It's the exact same thing with 1 plugged in. 2 to the 1 over 1 plus 1. Next, I'll add the same thing, 2 to the j, 2 squared over 2 plus 1. Where did I get the squared from? Because j equals 2. My last round, j equals 3. 2 cubed over 3 plus 1. Finally, I am going to evaluate each one of these, remembering the order of operations. So exponents come first, 1 over 0 plus 1, plus 2 over 1 plus 1, plus 4 over 2 plus 1, plus 8 over 3 plus 1. 2 cubed is 8. Now I can add and divide. 1 over 1 is 1, 2 over 2 is 1, 4 over 2 is 2, 8 over 3 is 8/3. Adding these up, I have 4 plus 8/3. That is the same as 12/3 plus 8/3 for my final answer of 20/3. The key to the summation is you add the same thing over and over again, but change the counting number. Let's try another example. This one is quite easy, but it could fool you. What's the sum from I equals 1 to 5 of the number 3? How do we do these problems? The first step is you're going to write all values of your variable. In this case, our variable starts at 1, I equals 1, I equals 2, I equals 3, I equals 4, and I equals 5. Each time we're adding 1, we go from the starting point to the end number. Now, what do we add? Each time we add this expression. In this case, our number is 3. Even though it doesn't depend on I at all, we will still add 3 each time. 3 plus 3 plus 3 plus 3 plus 3 is, you got it, 15. So that is summation notation. What's cool is that in the higher levels of math, we'll do summation notation with it going to infinity. And we'll add an infinite number of numbers and expressions and see what happens to it. What's great about that is that as we're computing this and as we're trying to figure it out, we also get to see how infinite God is and how beyond our imagination and beyond what we can ask or think or understand He is. So I would encourage you guys today to remember how great is our God, how amazingly infinite, powerful He is. And you'll do that as you're adding up these small terms now, which will soon grow to bigger terms. Next, we're going to do the linear regression part of our lesson, which will be over here. So, as you can see in this example, we have a bunch of points on a graph. Now, this helps us because in physics, biology, or chemistry, you will have a bunch of data that you perhaps collect for an experiment. And in order to make that data more understandable, you want to describe it using a line. Now, unfortunately, the line doesn't perfectly, there's no line that I could draw that would perfectly go through all of this data. In your book, they're going to give you an example of a line drawn in. I will redraw the line for your convenience. Now, the whole point of this problem is to take all of this data and all of the data in the table that they've given you and form the equation of a line with that data. How do we find the equation of the line? The easiest way, and you'll remember this from Algebra 2, is to find 2 points. Now, I will caution you with this. None of the points on your data normally fall on the line. And so, do not use these points in finding your line. You will get the wrong answer. Instead, look at the line that they've drawn and find points where it reasonably goes through the the graph paper here. In this case, I believe that that nicely goes through the grid lines, and this point here reasonably go through the grid lines. Another word of caution, choose your points as far away as possible. So even though I could choose these 2 points, I also see that it goes through this point way out here. The further apart you choose your points, the better answers you're going to get. So, as a side note, choose far away. If you choose 2 points that are close to each other, you could get a really bad answer. For example, that's a really good graph and a good estimation of what this graph should look like. But suppose I chose 2 of the wrong points. Look at how differently this graph would look. See how that graph misses these points up here? So it's very important that you choose points that are far away as you describe your line. In a future lesson, we're going to learn that your graphing calculator can do this for you. So for now, bear with it, and in a moment, or in a couple of weeks, you'll be able to do this and get the most precise and best answer. For now, we'll guess. So what 2 points do I want to choose? Well, I chose this point, whose x value is 40. Y value is, now be careful, because the scale is always weird on these problems. In this case, it does go 0, 2, 4, 6, but sometimes it won't start at 0. So in this case, I have x value 40, y value 0. This point, if I look over here, is at 160, y value 10. After you found 2 points, how do you find the equation of the line? Well, let's move over here and find out. You can find the equation of the line by finding the slope. The equation for slope that you should have in your notes is m equals y2 minus y1 over x2 minus x1. Now that we've found our points, we don't have to worry about the graph anymore. So we'll move over here slightly. My 2 points were 40, 0, and 160, 10. So y2 is 10, y1 is 0, x2 is 160, x1 is 140. Pardon, 40. Make sure you do the same order each time. So if this is y2, it must also be x2. If this is x1, this one must be y1. This is 0.2, this is 0.1. Solving this for the slope, I get 10 over 120, or 1/12. From there, we'll take the slope and find the y-intercept. We know that y equals mx plus b, so we can plug in our slope. Since I'm trying to find b, I will also need an x and y point. All right, finally, we are going to plug in this point, 40, 0, and solve for b. Subtracting, well, we can cancel. That looks like 20 over 6 and 10 thirds. Subtracting 10 thirds from both sides, b equals negative 10 thirds. So our final answer again is going to be in y equals mx plus b form, and is going to be y equals our slope, which was 1/12, x minus 10 thirds. Now, one word of caution, and something that you should keep an eye out on, is over here at our graph again. If you notice, they're measuring the amount of salt versus the amount of carbon. And they give us variables C and S for carbon and salt. So over here with our answer, we should write our answer in those terms. Since the y-axis is salt, my answer should be salt equals 1/12 carbon minus 10/3. Always pay attention to what values they're talking about so that you can write the answer in the correct form. To recap, you'll find 2 points, not the ones listed in the table. Choose the points as far away as possible from each other. Then find the slope using this equation right here. y2 minus y1 equals x2 minus x1. Then find your y-intercept. This is all review from algebra. Finally, you write the answer not in terms of y and x, but in terms of the variables that they give you. Now, the last part of our lesson is quite quick and fun. So, this is decomposing functions. The key here is that you are looking for one function that is inside of another. So, their first example is that they want you to find two functions such that f composite g of x is the square root of x squared plus 1. What you are doing in these problems is you are trying to find the outside function and the inside function. See how x squared plus 1 is completely inside of the square root? That makes the square root my outside function, which will be the one furthest away, in this case f, and the one inside is the one closest to the x, which is g. How would I write this? Well, my inside function is easy. G of x equals x squared plus 1, the function that's inside, and f of x is the outside function, the square root. But I must put something inside the square root. Instead of writing x squared plus 1, I replace it with x. That way, my outside function is defined in terms of x, and my inside function is defined. What happens when I plug in g of x inside of f of x? I get my original. So, inside function, write the inside function. Outside function, take that outside function, and where the inside function was, plug in x. Let's try another example. Goodbye, wonderful graph. Suppose we have f composite g, that means f is eating g of x, and that equals 1 over x squared plus 1. What function is inside in this case? Well, the inside function is x squared plus 1 because it's inside of the 1 over function. So my inside function is easy. G of x equals x squared plus 1. And the outside function is a little bit more challenging. It's 1 over, and instead of the inside function, we replace it with x. Your answer for these decomposing functions problems is right there. And that is lesson 34.